y'all to give that like bar energy. So yeah, like please ask questions at any time, raise your hand, shout it out. That would help me out a lot. So yeah, thank you for the intro. I'm really excited to be here. This is so cool. Just the opportunity to like talk about space and the stuff that I learned in my career at NASA and figure out how to navigate this projector. So we're gonna make it happen. So yeah, like Jonathan said, I'm an instructor of mechanical and aerospace engineering at UCF, but that comes after several years of working out at NASA. So I'm going to talk a bit about myself, so you know who you're hearing from. I'll define some learning goals, some things that I want y'all to like leave with, and then we'll just do a crash course. We're gonna go right into Astrodynamics. You're gonna learn like some things that it may take students like weeks and weeks to learn in just like 20 minutes. So buckle up. And we're gonna talk about some space science missions, because I think that's the fun stuff, right? So we'll get right into it. It's a little hard to see this image because it's kind of like dark, but does anybody know who, does anybody know who this icon is? Like who this?
Donald?
Well, okay, yes, it's Donald Glover, but who the character is? It's not Atlanta. Does anybody remember the name? Like what's this from? He's the Astrodynamicist from The Martian, right? So I don't know when the book came out, but I was reading it in 2015 or 2016, which is around the same time that the movie came out. And it was really fun because I was like 3 years into my astrodynamics journey at that time. I took my first class in 2013 and I fell in love with this stuff. I thought it was so cool. Like that was the first thing in my undergrad education that I was like, I want to know everything about that. And I'm reading this sci-fi book, and the astrodynamicist, I mean, this is kind of a spoiler, so I guess if you haven't read or seen The Martian, which is a movie that came out 10 years ago, you know, maybe cover your ears. But yeah, the astrodynamicist saves the day, and it was like the coolest thing to read that in the book. And then, yeah, the character in the movie was Donald Glover, so I loved that. So yeah, I was like, I want to be a person like that. I want to be a mission designer. And this is a little bit of what my career has actually looked like. So it's kind of out of order, but I basically got to do a lot of launch stuff, working out at Kennedy Space Center, because that's what we do here in Florida. We know that there's a ton of NASA centers all around the country, and here we specialize in launches. So this one here at the top, that was back in 2020 when we launched the Perseverance rover. Are people familiar with that rover? Does anybody know like what else went along with Perseverance? Like was there another like spacecraft? Maybe anybody remember the name of the helicopter? Yeah, the Ingenuity helicopter. So that was the first helicopter to fly around on another planet. So that was on the underbelly of the Perseverance rover. And I got to be a part of launching it. That was a super cool experience, and I'll talk about what that was like. And then I really wanted to lean into my desire to educate. Obviously, I'm a full-time instructor at a college now, so that energy has always been there. But I actually moved and worked in like broadcasts and communications at NASA for a couple of years. So this is me on the Artemis 1, so not Artemis 2, the one that happened a couple of months ago, but the Artemis 1 broadcast when they sent just the spacecraft around the moon, didn't have any people in it. And I got to be a part of that, which is a super awesome experience. And I continued that work. So even when I went back to my technical job, I was still on broadcasts teaching people about orbit mechanics. You see the hula hoop. I've got a hula hoop here with me today. So like, this is what I do. This is what I love doing. And then yeah, this is me with the Europa Clipper launch vehicle back in 2024. And yeah, we'll talk more about what that was all about. So these are some of the goals that I have for y'all today. By the end, I want you all to be able to understand and explain just how orbits work, how stuff moves around in space, describe different types of orbits for space science missions, because it's one thing to say this is how an orbit works. It's another thing to say this is why we put a satellite into this kind of orbit. This is the science that comes out of it. This is what we can actually do with that information. And I want it to be kind of a catalyst, so you can do your own studies. You can understand what's going on around you. I mean, my friends know that anytime you're with me and I'm outside, I'm like, oh, look at that planet, or like, oh, look at the difference between the moon today and how it was last week. So like all this stuff is really ingrained in just the way that I see the world. I think that's one of the reasons why orbit mechanics is such an awesome field. So hopefully y'all can, kind of get the inspiration that I had from this field. And again, ask questions at any time. So this picture is really funny to me. It might not be funny to you yet, but these are the kind of diagrams that you see when you start studying orbit mechanics, and when you start talking to people who do this kind of work. All the words on here are complete nonsense. Like Determinant of the date of Easter, dimple of Venus. Like, it's just complete nonsense. This came from XKCD, the comic strip. And that's the kind of idea, like, a lot of people get confused. Even when you work at NASA, so many people don't know about orbits. Like, they know the details of what you're putting into space and all of that, but all the details of like how it actually works in space can be a mystery to a lot of them. So y'all may have a leg up on people who actually work at NASA and put these things into space. So who liked their physics classes in like their physics classes in high school or college? Yeah, who did not like your physics classes? Okay, so I'm curious, if you were to think of like one...
Speak up just a hair.
Speak up a little bit more? Yeah. Okay, is this better? I'll be a little closer.
You just drop off.
Gotcha, yeah, okay, thank you. So if you thought of like one equation that you remember from high school physics, what would that equation be?
E equals MC squared.
Oh, E equals MC squared, there's one. That's not the one I'm looking for. F equals MA, yeah, okay, so everybody remembers that one. One of the experiences I remember having in high school and college was like every year realizing that the thing that they taught you the year before like wasn't actually it. It was like, oh, we told you it was this, but it's actually this. So, you start getting more in depth into physics and orbits, and you realize that F equals MA is actually like this complicated vector equation. There's sums and everything like that. And I want to kind of, I feel like when people get away from school, equations become this thing that's like just super confusing. It's like, what even is that? So I want to sort of make it something that is understandable, and make sure people remember that when you look at an equation, it's just a statement. It's a statement of something that's true. So we're gonna like break these things apart for a few different equations that we're looking at. So for F equals MA, we really have two different pieces. So the left side of the equation is the dynamics. So that's basically what causes things to move the way that they move. And the other side is kinematics. So that's how the motion is described. So that is, what the actual path looks like regardless of what is causing that force. And you may recall like Newton's laws, like that sound, people are familiar with those. People may be less familiar with Kepler's laws, but that's where the kinematics come from. And those are going to be the two chunks, the two pieces of information that you're going to need to get in order to capture everything that I'm talking about today. So we'll start off with the dynamics. Okay, so we're losing the top a little bit, but so yeah, people are familiar with Newton's laws, equal and opposite reaction, inertia, all those kind of things. Oh, thank you very much. And that's okay if it's chopped a little bit. So all of these laws, he was able to develop this theory of gravitation that led to this equation down here that you may or may not be able to see very well. But you see F due to gravity is negative G, M1, M2 over R squared, R vector over R. So that is that theory of gravitation. And the idea is that you have two bodies, one with mass 1, one with mass 2, and there's a distance between them. And that distance is defined by R, just like a radius, it's a position vector. So what you're saying here is that the force on one body due to the other, caused by gravity, is going to be defined by this. And again, equations are just statements of truth, statements of what is happening. So what this tells you is that, one, gravity is a force of attraction. It's a negative force. So if the position vector is this way, the gravity force is going to be the other way. It tells you that the masses of both objects matter. So even if you're talking about like a small person on a satellite all the way out here, the Earth's mass is obviously way bigger, but that person's mass is going to be accounted for. The distance change is going to have a bigger impact than the mass change. So you see that there's a square here, so R squared is in the bottom. So if you like double your radius, you double the distance between the two objects, that's going to have a bigger impact than, say, doubling the mass of them, because that square is there. So if you look at an equation like this, you can just break it up into parts and say, okay, what's actually happening here? How can I gain some insight on what's happening just based on the equation itself? And lastly, this is universal. So this is the constant that just after taking a bunch of empirical data, there's a number that you can apply to everything. So all two objects have this gravitational force between them. So you and I, you two, everybody in here, everything is gravitationally impacting one another. And that's the case in space as well, right? So all of the planets are gravitationally interacting with the sun. They're all interacting with the Earth. So if you wanted to start defining those equations of motion to figure out why things are moving the way that they're moving, you would actually need to account for that. So here you can see like that sum of the force is going to include all the planets, all the moons, everything else that's out there if you wanted to be super, super accurate. Another thing that matters is that the Earth is not a perfect sphere. So does anybody know the term for like the shape of the Earth? I know that one person in this room knows it because I've said it to them before, but no, it's okay. Any guesses of like, if it's not a sphere, what shape it might be? An oblate spheroid, perfect. So it's a little squished because imagine a squishy ball spinning around super fast. It's gonna bulge out a little bit towards the center. So the equator is actually about 21 kilometers farther from the center of the Earth than the poles are. So it's a little squished. So if you were like a satellite trying to figure out what your orbit is gonna be like going around the Earth, there's like a little bit of changes in forces that you would have to account for. Another thing is that even though, so there's that, the general shape is an oblate spheroid, but also the Earth is kind of a lumpy mess. Like it's not even, of course. So I mean, and this makes sense, right? There's a bunch of mountain ranges up here. This is the deep ocean. So it's not even. So depending on where you are, the Earth is going to be pulling on you more or less than other places. So that's another sort of wrinkle that you would add to this force equation. So it's really piling up. If you want to get accurate, you have to include all of this stuff. And the last thing that I'll show, this may be a little hard to see, but so we're familiar that the Earth, is tilted relative to, the sun's plane. But if you zoom out, that tilt of the Earth that gives us our seasons, that is actually moving. So it's like a spinning top. So the Earth is like, it's basically drunk. Like it's not just spinning like this, but it's tilted and it's spinning like that. And that tilt is going back and forth. And so that period of motion, so that full circle is like 26,000 years. So that's a really, really long time. I don't really know all the implications of that, but what that tells me is that maybe the seasons would like shift over the next 10,000 years. Maybe northern hemisphere, summer would become winter, things would start to get a little weird. And then the smaller wobble is like 20 years, so that's a little bit less, that doesn't have as much of an impact. So again, that's just another wrinkle, another thing that you have to add. So you might be like, all right, what types of equations is Phillip about to show us? Like this is all that we're gonna talk about with those things, because we're gonna work with a more simple problem. It's called the two-body problem. So that allows us to ignore everything that we just talked about and assume that all that is happening is that there's Earth and there's a satellite, and those things are gravitationally interacting with one another. So this is called the two-body problem. As I said, you get these equations of motion that are basically saying accelerations, positions. It's describing how this position vector is going to change over time. And the important thing to note here is that you have this gravitational parameter mu. So mu is a Greek letter, I think it's a Greek letter mu. And it is a function of that gravitational constant and just the mass of the two bodies. So it's describing the strength of the force between them. So, all right, I guess this is the first time I'll say this. I've been saying a bunch of stuff, and I'm sure y'all are, you're hearing it. I think you're with me. I see some nodding heads. There's going to be trivia later, and I'll just give you a hint that something related to the trivia questions is on this slide right now. Okay, smart. I see phones coming up. But I think in trivia you're not allowed to have your phone out, so But yeah, so these are the gravitational parameters of all of the major bodies that we're going to talk about in the solar system. So you see the sun, it's like 1,000 times 10 to the 8. So that's 13, 27 with 8 or 9 zeros afterwards. But Earth is about 4,000 with just a couple more zeros after it. Oh, is it hard to see? Or? Okay. Maybe I should go over there so I can see the way y'all are seeing it, but okay, yeah, that's nice. Earth, so just think about the scales here. I'm not gonna ask anybody what these specific numbers are, but just think about the scales, you know. So you see Earth is like times 10 to the 2, so that's 100. The sun is times 10 to the 8, so it's like, you know, that many times bigger. You see that the Earth is about 100 times more massive than the moon. And you can see which ones, you know, Saturn is like 100 times more massive than the Earth. Jupiter is 10 times more massive than that. So you get some interesting insight into what's actually happening in our solar system. Okay, so that's it on the forces. Now we're going to talk about, does anybody remember what I said the other half of the equation was called? One half was dynamics, the other half was, oh, I kind of heard, the kinematics. Yeah, exactly. So now we're going to talk more about the kinematics. So do people remember geometry, like learning your geometry? Like, yeah, so we're going to get into geometry. So who likes geometry more than physics? Anybody? No? Oh, okay, there you go. Yeah. So basically Kepler, back in like the 1600s, he developed a bunch of laws based on observing planets and moons, looking up into the sky, taking data, and figuring out what's going on up there. And what he figured out is that orbits can be described as ellipses. Like all of these orbits he was looking at of planets orbiting the sun, moons orbiting planets, it was always an ellipse, which is the shape that you're looking at. And ellipses can be categorized or described with an eccentricity, so that describes the shape, like how oblong or circular it is. The semi-major axis is basically the average radius. So radius from the center of the planet to the position of the body. So, you know, here the radius is super short. When it comes over here, it's super long. The average value is the semi-major axis, and then the true anomaly is the angular location. So it's like 0 right here, it's 90 over here, 180. So those are the parameters that matter, and those are just geometric. It's just geometry. This is another way of seeing what that looks like. Unfortunately, it flipped direction. Hopefully that's not confusing. But what you can see here is that if you have an eccentricity of 0, you have a circle. So E equals 0 means it's a circle. So the average radius is just the radius. It's always going to be the same distance from the center. And you can define the amount of time it takes to go around it based on that radius. Like that, those are two parameters that are intimately connected. So what that tells you is that even if you have a different shape, you can have one super elliptical, highly eccentric orbit, but if they have the same, if its average radius is the same as this circle, it's going to have the exact same orbital period. So you see these things are lining up right here. If this one's going really slow, this one's a bit faster, but then that's about to start to switch, because as this one starts to come around, it'll speed up over here, and then they'll line up again. Hopefully y'all saw that on the other side. So you learned some interesting things about how orbits work and how they relate to one another. So yeah, here's the other one speeding up. That's the true anomaly, getting closer and closer to 0, and then boom, it's at 0, and then now it's going down to -90. And so yeah, what this tells us is that pretty simple geometry can help us explain paths driven by gravity. So you have a parabola. People remember that shape, right? You know, quadratic function. So that looks like this path. We have a hyperbola, which looks really similar, but you can maybe tell the difference here. Instead of sort of curving around, it's really sort of following an asymptote. So it's like a straight line here, then it starts to curve, and then it's another straight line. And then the ones I talked about before, a circle and an ellipse. If your eccentricity is 0, you're a circle, and if you're in between 0 and 1, you're an ellipse. How am I doing on time? What time is it?
Oh, 7:22.
Okay, cool, thank you. Okay, so like I said, simple geometry. This is just sort of an interesting piece that comes out of this is that we call it conic sections, because if you imagine taking a cone, so like this red cone right here, and then you take a plane and you slice open that cone, and then look down on that plane and see what shape you will get the possible shapes of an orbit. So it'll be a circle if it's like perfectly aligned. If you have a sort of an inclined plane there, you'd have an ellipse. If you have it inclined even more to a very specific angle, you'd have a parabola. And then if your plane was perfectly straight, perpendicular to the bottom of that cone, you would have a hyperbola. Okay, so that was a big step. We talked about the size and the shape of an orbit. So the last thing we have to do is talk about the orientation of that orbit. So this is where there's a ton of really confusing sounding words: vernal equinox, vector, ascending node, perigee, apogee, equatorial planes, all that kind of stuff. So like instead of going into all that, I'm gonna start to use my visual aids. So we're gonna use my hula hoop. This might be hard to do with the microphone, but I need a volunteer. Can someone be the earth, please? Please, okay, thank you. Let's give a round of applause to our volunteer, please. Okay, so can you hold the microphone up to my, this is crazy, but actually that might not work either. So, yeah, we'll do this. Okay, so.
I could be your mic stand.
Oh, thank you very much. Yeah, okay. So we talked about, ellipse, if it's more like this or stretched out. Can you like line it up where the North Pole is up? Yeah, okay. So if you have an orbit that's like this, you have a low inclination. It's not inclined. If you incline it like this, that's a higher inclination. So that's your I. So that is this one, inclination. Your arguments of perigee, so the perigee is the closest point between the center of the Earth and the orbit. So like if it comes really close and then it goes far away, that perigee points, how that is rotated around, that's gonna be your argument of perigee. And then the last thing is your longitude of the ascending node. So that is if I were to take the orbit and twist it around this way. That's basically defining those last three. So you can imagine there's 3 parameters describing the shape and the size of the orbit, and then 3 parameters describing the orientation of the orbit. And that's all you need to do to fully define, thank you very much for doing that.
Yeah, of course.
Very difficult with the mic, but we're making it happen. That's basically going to fully define what's happening with an orbit. So the reason why I told you all about the conic sections is because that's actually something we can use to design missions to other planets. So if you take that 2-body problem that we talked about, we say all we care about is 1 planet and 1 satellite, you can start to basically work like puzzle pieces and just patch things together. So you can have 1 conic that's over here that has your 2-body problem related to the Earth, and you describe, some hyperbola leaving the Earth. You identify times, speeds, directions, and then you say, okay, we're done with that. Now I'm just going to take that direction and make that be the starting point for my new 2-body problem, where what matters is the sun in that spacecraft that I'm talking about, and it's following that trajectory. Now what matters is the distance between the spacecraft and the sun, and then as you get closer to Mars, you can do the same thing again and a whole nother 2-body problem. So this is how you can take very complex things that are happening and just breaking them up into smaller chunks and figure out some really interesting paths. So, and then here we kind of lost it at the bottom, but what I'm showing you here is that C3, these are basically new parameters that you can use to define an outbound trajectory, something that is not a closed orbit. So if you're leaving a planet, you would basically define C3, which is your energy of like how fast you're going when you leave. Declination is like kind of like a latitude. It's like, are you going high up or low down? And right ascension is like a longitude. Which direction are you going in that way? So now I'm like done with the theory, and we're going to see what it looks like with real missions. So you're trying to get from the Earth to Mars. Maybe kind of hard to see Mars right here. But 1 Mars year is a little bit less than 2 Earth years. I think it's like 687 days or something like that. So there's a cycle. It's a repeated cycle. So basically we can figure out there are windows of time when it's easier to do that transfer between the 2 planets, just because of the way that they're lining up. So when you do that patched convex problem, you can create something called a pork chop plot. You look at this and it's like, well, does it look like a pork chop? I don't know. But that's what we call it, because it's basically giving you contours where you can say, okay, on this date, if I were to leave Earth and try to get to Mars on this date, how much energy would it take me by setting up those different conic sections or those different patched conics problems. And you can figure out good time windows for your interplanetary missions. So this is what the real porkchop plot looked like for Mars 2020. So this is the trajectory that I worked with for several years. It's so interesting that this chart is still a part of my life now. But yeah, you can see the departure date is down here. So this is like July of 2020. The arrival date in December, January, February, March of 2021. And you see all these different things that they attach to this. So like DTE is direct to Earth communication capability. Over here, they're talking about the end of the dust season. So, you know, you're trying to design this mission and figure out the perfect time to literally throw something off of the Earth and put it on another planet. And there's all these things that come into factor, but again, it's just piece by piece. And some story comes together that says, oh, this is a good set of dates when we can depart and make it happen. So that's the power of some of the stuff that y'all have learned about today. I'll skip past this. This is just more of the numbers of what that looked like and what that outbound trajectory was. And yeah, this is the animation of what that final path looked like. So you see how it sort of took advantage of that synchronicity between the Earth and Mars. You see how it sort of slowly approaches Mars and then is able to land there. And now we can see what that looked like for some other missions. So Psyche is the name of a spacecraft that's going to study an all-metal asteroid, or it's an asteroid that we think is fully made of metal, which is interesting, right? Like most asteroids are rocks. Like we assume that they're rocky, but scientists think that this one is made of metal, which would be super different. So they're sending something out to go study it, and we actually used one of those hyperbola trajectories to get there. So you can see here the blue is Earth, the lighter blue, the cyan, is Mars, and then the green is the asteroid that it's trying to get to. And I'll wait for it to start over one more time, and we can see that Mars flyby. So here we're going. It's coming out pretty far, and then it's swooping back in and flying by Mars right there. So that's where the hyperbola happens. And man, it's a little dark, but hopefully you can see this. So this is an animation from this website called eyes.nasa.gov, where they simulate like everything that's in the solar system right now. It's so cool. So if there's anything you take away from this, go to eyes.nasa.gov and just check out what they've got going on over there. So they simulated it. And literally like 2 weeks ago, it actually happened. So, you know, look, like that's the animation, that's the real photo. Like that's the picture from a spacecraft that was flying by Mars. And again, there's the animation, there's the real photo on the way out. So that's pretty cool to me. Europa Clipper, similar thing. You saw it launch, it did a really quick Mars flyby, and this is the animation of what that one looked like compared to some photos that they got back in March of last year, right? Yeah, March of last year. So they got a picture of Mars and Mars's moons. So pretty cool chance to like calibrate your instruments and, you know, test things out before they get to their final destination. And the exciting thing here, I lost some text, but Clipper is actually going to fly by Earth in December of this year. So the thing that we launched in October of 2024 flew out by Mars, swooped back in, and is going to fly back by Earth one more time in order to complete its trajectory to get out to Jupiter. I think I meant to have the full path, but then I may not have that there. So that's something to look out for. December 3rd is when Clipper is going to fly back by Earth. And then I'll just talk about a couple more types of orbits beyond the interplanetary trajectories, because these are the ones that really like bring it home and help us see like the value of some of this work that's going on. So you can have a geostationary orbit that gives you uninterrupted views of one region. So I think we can all relate to this because we live in Florida where hurricanes matter. So this was Hurricane Milton that flew by right before Europa Clipper launched, and it was imaged by a geostationary satellite that, you know, my team had launched just a few months before that. So this is where, again, taking that simple information that I gave you earlier about how you can relate the radius of the orbit to the period. All you have to do is create a circular orbit where the period is 24 hours, And as I am the Earth and I'm rotating around, if I have a satellite all the way out here that's also taking 24 hours to go around, it's always going to be looking at the same location. A sun-synchronous orbit is basically one where you can sync up with the geometry of the sun to have the same sort of lighting conditions, the same time conditions, and that gives us really good climate pattern data. So information that you may see like this, where you can see like the bands, like clearly something is passing over like north to south. That is enabled by sun-synchronous orbits. And then this last one is definitely the most complicated one. And I feel like I'm probably short on time, so I'll only talk about it a little bit. But basically, there's special orbits that you can get in that allow you to sort of park in between different bodies that are moving around. So it gets super complicated. If you can see here, you basically have this like deep gravity well. Like if you get close to the sun, you're going to come into the sun. If you get really close to the Earth, you're going to be gravitationally, dominated by the Earth, and you get closer to it. But there's some really like finessed spots, like right here. If you get in the right speed and direction, you can like park right in between those places. So if you do that, you can do something like this. So this is real images from a spacecraft that's like 1 million miles away from the Earth. That's where that Lagrange point is. And you can just watch the moon pass by, because you're just parked right there between the sun and the Earth. And another really important one that we just launched is called SWIFO, or Space Weather Follow-On. And it's parked also between the sun and the Earth. And it's an early warning system for solar flares. So if the sun ends up shooting out a big solar flare that has the opportunity to, take down the grid, we can have like 7 or 8 minutes of warning time, because there's something 1 million miles away that would detect it, have all the data, and send it to networks here on Earth that would be able to shut down things that would otherwise be damaged. And lastly, there are things just in nature that are taking advantage of these points. So there are, asteroids that are just parked. I'm actually going to step back a couple of slides. So there's these ones in between, but there's also these angled points. So these are also like sort of equilibrium points. And there are asteroids that are just parked out there for the Sun-Jupiter Lagrange points that have been there like for a very, very long time, because they're not getting flung around to other places of the solar system. So that helps us understand like the origins of things, because those satellites are really, really old. So this is my last real slide, because this is showing the trajectory of a mission called Lucy, which also launched several years ago. I think like 2017 or 2018 or something like that. And it's basically navigating that whole space between in the Sun-Jupiter frame, where it's saying, hey, we want to go study some asteroids that are out here at L4 and some that are over here at L5. So what you're looking at on the left side is like a view if you were to just step outside of the solar system and look at everything move. But this view is if you were parked at Jupiter and you were watching this big clump of asteroids over here and this big clump of asteroids over here, and you can see Lucy's path as it's navigating that really complicated trajectory. So it's all super complicated, but this all stems from the same foundations that, I think a lot of you already understand from this presentation. So that's about all I have. Any questions about any of that complicated mumbo jumbo?
Do we have any questions for our speaker? I will give you this microphone. Oh, sure. Find the other one.
Can Astrodynamics explain why Uranus planet is kind of on its side when it's orbiting?
That's a good question. I don't think Astrodynamics explains why Uranus is like tilted. I think planetary science does that more, because I feel like there's probably models of how that happens. But I think what Astrodynamics tells you is that obviously something strange happened for that to get there, because everything else is, we sort of assume that it came from this disk, everything is moving in the same direction. Something probably just knocked Uranus over. I don't know what the real theories are, but yeah, it's a good question. What other questions?
Testing. Oh, this is very loud. Okay, let's turn the mic over here.
This might be a little outside of your presentation, but you mentioned that the solar radiation early warning system would give you like 8 minutes of warning. How would it do that if the solar radiation is traveling at the speed of light and that would travel at the speed of light?
Yeah, because it's not. So it's not radiation. It's not just light. It's a solar flare. So there's like physical particles that are not coming out at the speed of light. So I don't know exactly what the speed is, but I heard somebody say 8 minutes. So it's whatever speed correlates to 1 million miles away, and it takes 8 minutes to get there. So but yeah, that's a really good question.
Do we have any more questions for our speaker? I just have a general curiosity question.
Yeah.
Is JWST sitting in the L3 spot?
That's a good, JWST should be in L2, right? Oh, yeah, so yeah, the James Webb Space Telescope is out here at L2, so it's, Sun, Earth, James Webb, so it's able to look away and not have a bunch of noise, so you're trying to study other stars, get really accurate data. You can't have the super loud sun, interrupting your telescope, so that's why they park it on that end.
Cool, thank you. Let's give our speaker another round of applause.
This is one.
My first AOT was about the Martian, so it's very fun to come back to Project Hail Mary. I am a planetary scientist by trade, and I'm a postdoctoral research scholar at UCF. So I'm going to give a little bit of my background, especially for the kids in the audience, so that you can kind of see the path that I followed to get to where I am. So I went to high school in a really tiny town in Tennessee. I did not take calculus. The highest math I had was pre-cal. And I took trig-based physics. So you can, in fact, get into college and succeed without taking a bunch of AP classes and doing a bunch of other stuff. I did my bachelorette, there you go. I got my bachelor's degree at the University of Alabama in Huntsville, where I got a BS in physics with concentrations in astrophysics and optics. So that's the physics of the stars and the physics of light. And that was in 2020. And then I moved here. And last year I got my PhD in physics in the planetary sciences track at UCF. So that's kind of the way I went. Planetary science is really cool. It's better than astrophysics. And if you like astrophysics more, I'm really sorry. So a little bit more about my scientific background. I study airless bodies, so that's exactly what it sounds like. Planetary bodies that don't have atmospheres, like the moon and Mercury and asteroids. And all of these bodies look really gray and really boring, but I promise you they are fascinating. I look at their composition, their surface properties, and their surface processes, so the things that change them over time, including space weathering, which we're going to talk about a lot, because it's very relevant in Hail Mary. I love dirt. There are so many ways to look at it. I love planet dirt. And two ways that I look at it are through spectroscopy and microscopy. So spectroscopy looks at how light and matter interact. So we get absorption, emission, reflection. And in microscopy, we stare at the super tiny stuff. I specifically look at electron microscopy, so I look at the surface of super tiny things and through super tiny things to figure out how their physical properties change their optical properties. So we tie those two things together. And both of those tools are used in the movie to analyze a very wonderful, important thing in the movie, which means that I immediately had a lot of thoughts as soon as I started watching the movie. But a disclaimer before I get into this is that I'm not a microbiologist, and I have a 9th grade understanding of biology, so please don't hold that against me. We're also kind of going to get into the sci-fi versus fantasy thing tonight. Andy Weir really loves to say that he writes hard science fiction, and he does. He tries to make his fake math as real as possible, which is really awesome. And he's quoted in the New York Times as saying that he's super proud that the only true violation of physics in this story is something you have to go down to the quantum level to find. Now, some would argue that that is still a violation of physics. However, we'll move forward. At this point, If you haven't read the book or watched the movie, go outside, go to the bar and get like 6 beers, get really drunk so that you forget everything that I tell you, or plug your ears maybe. So I'm going to do a little Cliff Notes edition of Project Hail Mary to prep us for the science. So basically, Project Hail Mary starts because humans observe this ribbon of infrared light connecting the sun and Venus, and they call it the Petrova line. And at the same time, they notice that the sun is exponentially dimming, and it's so bad that the Earth is going to enter an ice age in like 30 years, and everybody's going to kill each other, and it's going to be a really bad time. So they send a probe to sample the Petrova line, and they find this alien eukaryotic cell that they call astrophage, or star eater. And also, every other star is dying too, except for a special one called Tau Ceti. So the world decides to send a one-way mission to Tau Ceti to see what makes it so special. And the only guy who wakes up when the ship arrives is a middle school science teacher with amnesia and a really big dependency on duct tape. So, Dr. Ryland Grace, in this mission, must overcome his crippling imposter syndrome and memory loss to save the stars with an alien that he meets at Tau Ceti named Rocky. Amaze, amaze, amaze. Rocky is from the 40 Eridani system, and he interacts with Dr. Ryland Grace using echolocation and music. And they learn how to communicate and sample the astrophage in Tau Ceti's Petrova line to see if it's the same or if it's fundamentally different from the astrophage in their own Petrova lines. So they sample an exoplanet around Tau Ceti, called Tau Ceti E, or Adrian, and they find an active biosphere with an astrophage predator called Taumoeba. They breed the Taumoeba, they save the stars, there's a happy ending, but there's a lot of stuff that is very interesting along the way that we have to talk about. Another disclaimer, I think this movie's really awesome, and I love Andy Weir, he's a great science fiction author, and I'm not here to crush anyone's dreams of interstellar travel or conquering the universe or anything, so please don't beat me up in the parking lot after this. And we can't tackle it all. There's a lot that the science doesn't get quite right in this movie, but here's the stuff that made me really freak out the most. We're going to talk about astrophage. We're going to talk about the fact that every star was dying. We're going to touch on xenonite, and then we're going to have a rapid fire round where I talk about all the dialogue that made me cringe really hard. Then we're going to talk about radiation sickness, which is a problem for humans, not just Iridians. And at the end, we're going to touch on relativity and time dilation and how long you can really be in a coma. All right, so let's start with astrophage, which is a perfect battery. I'll talk a little bit about what that means in a second. But before we get into that, I feel like it's important that everyone knows or has at least heard of the electromagnetic spectrum. Raise your hand if you know what the electromagnetic spectrum is. Okay, slay. All right, so the electromagnetic spectrum sort of describes all of the different kinds of light in the universe. The light that we can see is visible light to us, which are all these colors that you can see here. But there's other types of light, like radio waves, microwaves, infrared light, there's ultraviolet light, X-rays, gamma rays, all of these things that we sort of know about in our daily life, but we don't quite think about in terms of the universe. So infrared light is a really, really big part of this story, so I wanted to sort of touch on that first. Infrared light is very small, it's about the tip of a needle point, is the wavelength of that kind of light, so we're looking at things that are that size. All right, now let's get into astrophage a little bit. So astrophage functions off of Einstein's super famous energy balance equation, E equals mc squared. It basically absorbs energy from its host star, converts it to mass, and converts that mass back to energy to use it for light speed interstellar travel. And that's how it gets all around to every star system that we're looking at. And it acts as a perfect battery by trapping neutrinos. And we're going to talk about what that means in a second, but everyone who knows what a neutrino is like, right, okay. So when astrophage releases its energy, it releases infrared light, and that's why we see the Petrova line between the sun and Venus. And that happens at 25.894 microns, which is an entirely made up number. There is no known like emission like thing there that has to do with carbon or water or anything. But let's get into the neutrino thing, since I brought that up. Neutrinos are primarily made by nuclear fusion inside the sun. So we take a hydrogen and a hydrogen and we stick them together, and that makes deuterium. And from that, you get a neutrino and a positron. And so on and so forth until you fuse hydrogen into helium, and then you have the actual power of the sun. The cool thing about neutrinos is that they are basically massless and they are chargeless. So they don't interact with anything. There are trillions of neutrinos passing through you right now, and you would have no idea because they don't interact with you. But they interact with the astrophage, and the astrophage can trap them and use them for energy. And how does that work? It's made up. Andy Weir invented this term called super cross-sectionality that does not allow for quantum tunneling to occur. And you're probably saying, Autumn, what the hell is quantum tunneling? It's how stars shine, and if we think about it in a physical sense, imagine I walk over to the wall and I try to bash my head through it. There's like an energy barrier there that I have to meet in order to like slam my head through the wall. But light is really cool because it acts as two different things. What are those two different things? Yes, a wave and a particle. So there is a probability function that determines where light is going to be, right? And so if I were a particle of light, I could clip through the wall, which is pretty cool if I really felt like it. And every once in a while that happens. And that's what allows nuclear fusion to occur inside the sun. Hydrogen is positive, right? Hydrogen over here is positive. Slam them together because they're around in the same place. They don't want to be together, but the gravity of the sun pushes them together and then they fuse. But yeah, so basically Andy Weir says astrophage doesn't allow for quantum tunneling. Okay, awesome, cool. That's how he explains most of the magic of the book and the movie after this point. Astrophage is completely opaque. It doesn't let any light through it. But realistically, in actual life, radio waves and microwaves, which are bigger than the size of the 10 micron astrophage cell, would diffract around it. So they would not be absorbed by the astrophage in real life as they are in the movie. So, another thing I want to mention about astrophage is that nothing we know of could survive the temperature of the solar corona. Astrophage is said to live on the sun in the movie, but the temperature of the solar corona is anywhere from 1 to 10 million degrees Fahrenheit, and the limit, as we know it, is 252 degrees Fahrenheit. So shout out to this little microbe that I don't know how to pronounce. They live in hydrothermal vents at the bottom of the ocean. Okay, we've talked a little bit about astrophage and its fake made-up properties. And also, no star is safe from it because astrophage needs CO2 to breed and make more of itself. In our solar system, carbon dioxide-rich atmospheres are pretty common. We have one on Venus, which is currently being destroyed by the astrophage, or consumed by the astrophage. And then Mars also has a CO2-rich atmosphere. And here's a little aside to the Martian. Interestingly, in the movie, it appears that every single star is being destroyed by astrophage, which means that every single star must have a carbon dioxide-rich exoplanet orbiting it. But how realistic is that actually? So carbon dioxide is pretty common in the solar system, like I said, and we know of over 6,000 confirmed exoplanets in 4,800 star systems. There is an observational bias when it comes to detecting exoplanets. It's easier to see bigger planets because they are bigger, and those are usually gas giants. So that's stuff like Jupiter and Saturn that's made out of hydrogen and helium. Because of telescopes like the James Webb Space Telescope, we now have 10 known exoplanets with carbon dioxide in their atmospheres, like WASP-39b, which is 700 light years away. But how do we detect carbon dioxide? How do we figure out if that is actually present in an atmosphere? we use infrared light, which again, we were talking about earlier. Each chemical bond in a molecule vibrates at a specific frequency, so we can use all of these different kinds of vibrations to perform spectroscopy and find where these molecules are interacting with light. So stretching, scissoring, twisting, rocking, wagging, all of these types of movements create different absorption features in the spectrum. Each dip and peak you see here has meaning, and this is a spectrum of exoplanet K218b. It shows methane, carbon dioxide, dimethyl sulfide in its atmosphere. We see the wavelength in the infrared on the x-axis, and on the y we have the amount of light that's actually blocked by the atmosphere. So we do know that carbon dioxide-rich atmospheres can exist in exoplanets, but how likely is it that every single planet, or every single star has a planet with a carbon dioxide-rich atmosphere? Maybe not super. But at the time of writing the novel, we have to give Andy Weir his credit. Tau Ceti was believed to host 5 exoplanets. Tau Ceti is a star with almost the same mass as the sun, but about half of its luminosity. And the exoplanets around it at the time were detected using the radial velocity method, which is where the sun and the exoplanet orbit around each other. It changes the way that we see the light here on Earth, and that gives us a clue to say, oh, there's an exoplanet in this system, or in this case, more than one. But it turned out last year there was a paper released that they attributed this to stellar cycling instead. But each star has a cycle. Our own star has a cycle, an 11-year solar cycle at that, where it goes through periods of minimum and maximum activity. So sometimes those changes in brightness that we see in stars can be attributed to exoplanets instead of just regular variations in the star itself. And the same thing happens with 40 Eridani, which is the system for Rocky. There was a super-Earth candidate in the habitable zone around 40 Eridani. And the habitable zone is where liquid water can exist on the planetary surface. Vulcan is supposed to orbit 40 Eridani, so everyone got super excited, and they were like, oh my god, the planet Vulcan might exist. But this has since been disproven, also because of stellar cycles. So this is very sad. Next topic is xenonite, which is just unobtainium part 2, and this part really got to me. As we know, at standard temperature and pressure here on Earth, xenon is a gas. Does anyone know what kind of gas xenon is? Noble gas, yeah. So it doesn't want to do anything with anybody. It definitely doesn't want to make any crazy compounds to work with in space. At least here on Earth, who knows? On Earth and on the Hail Mary, we're operating under standard temperature and pressure, right? So 72 degrees Fahrenheit, 1 atmosphere of pressure to keep us comfortable. On Arid, Arid is said to have a temperature of 410 degrees Fahrenheit and a pressure of 29 atmospheres. So that's 29 times the pressure that you're experiencing right now. So maybe, in some cases, xenon can exist, not as a gas, but not on Arid or Earth. If we look at this plot here, which is called a triple point diagram, on the x-axis we have temperature in kelvins, and for the Kelvin challenge, like myself, I put the degrees in Fahrenheit here too. On the y-axis is pressure. You can see this little picture of Dr. Ryland Grace. This is where we're sitting throughout the entirety of the movie for where xenon should be. So right, it's a gas, cool. But if you get cold enough, so like negative 280 degrees Fahrenheit, or a super high pressure and a little bit warmer, you can have solid xenon. But imagine if we take the temperature up to 410 degrees, xenon's definitely not going to be a solid on Arid. So this is just a fake material, which is sad. You just can't question it. It makes the plot move forward. But even as a solid, which we have made solid xenon a few times here on Earth, It's not malleable or ductile or magnetic, and it's a pretty poor conductor. I did look online, and some material scientists on the internet are like, you could make xenonite with carbon nanotubes and some kind of biopolymer that only exists on arid. And I'm like, okay, that doesn't help me at all. It's also not real. But one more question I have about the xenonite that really bothered me in the movie was, when we think about launching things into space, we think a lot about weight. How much are we taking with us? In the book, Rocky had enough xenonite to make a 10-kilometer long chain, and in the movie he had enough to make a 5-kilometer long chain and also build all of his like hamster balls and like everything else that was going down. So that's a lot of extra material to bring with you when you're in space. And like, for reference, 5 kilometers of chain is like if you walked the World Showcase at Epcot like 3 times. So it's a significant amount of material that they just had left on the ship, which probably wouldn't happen in regular space travel. All right, now we're gonna have our little rapid fire round, which is where I talk about little throwaway bits of dialogue that got to me. So one of the first things that Dr. Riley Grace says when he wakes up is that an atomic resolution scanning electron microscope? Why do I know that? Am I smart? Scanning electron microscopes do not achieve atomic resolution, but transmission electron microscopes do. So in this figure here on the left, you can see some views of a mineral called olivine, which is the gemstone pyridoid. It's one of the most common minerals we have on terrestrial planets. You can see scanning electron microscopy hits the surface, and a beam of electrons is scanned across the surface of the material, and so you get an image of the outside of it. But in transmission electron microscopy, you can go through the sample and look at its atomic structure. So that was a little bit of dialogue that really got me, especially as a microscopist myself. The next one was that a radio telescope enthusiast discovered a beam of infrared light. And if there are other observers in the room, you know that we stay in our lanes. A radio astronomer would not be using an infrared instrument. You can switch it up. Some of us do, most of us don't. All of these instruments behave really differently. The data analysis process is very different, and we're all looking at really different things when we're studying different wavelengths of light, as shown here with all of these different images of the Crab Nebula. So that one also kind of got me. I was like, why was a radio astronomer using an infrared telescope? And the last line of dialogue that really got me, or not dialogue, this scene here was kind of crazy. I'm not a biologist, but centrifuges spin at thousands of rotations per minute to separate particles out when you're trying to look at DNA and things like that. But if you don't balance your centrifuge properly, you can break all of your equipment, and like the glass will break and like the motor will catch on fire and like fly everywhere. So we have a lot of OSHA violations going on the Hail Mary. All my homies died at work today. Not that the Hail Mary was safe to begin with, but. All right, the last thing that we're gonna touch on is radiation sickness. It sort of ties into the coma at the end. Radiation sickness is not just an iridium problem. In the movie, we saw that Rocky was the ship's engineer, and his lab was next to the fuel tanks for the ship. The astrophage there absorbed all of the radiation, which again is that fake super cross-sectionality property that we were talking about. So the fake astrophage science saved Rocky's life. This is amazing. But it didn't save everyone else. Radiation from space causes significant DNA damage, which is a big yikes, and then you get mega cancer and then you die. But Iridians didn't know about radiation because they are blind to light as they live under a 29 atmosphere, and their planet has a really, really strong magnetosphere, which blocks the solar wind and cosmic radiation. And you're probably saying, Autumn, what is any of that? Well, we have a really strong magnetosphere here on Earth that protects us from solar radiation as well. So the solar wind is a stream of charged particles that is constantly bombarding everything in the solar system. But there is a dynamo inside Earth. Our core and the mantle are convecting and causing a magnetic field to form around our planet. And that holds our atmosphere in place and protects us from the solar wind. it's also what causes the aurora here on Earth. So when the solar wind is captured by a magnetic field line on Earth, it gets funneled down to the magnetic poles of the planet. It ionizes the gas inside our atmosphere and then causes all those pretty colors. So that's why last year, year before, whenever we had a bunch of solar storms, people were seeing the aurora in like Tennessee and Alabama because all of those solar energetic particles were bombarding the magnetosphere and causing it to move and shift. And so we were seeing the aurora in different places. All right, so Rocky was saved by the astrophage on his ship, but the Hail Mary does not have the same anti-cancer layout that the Blip A did. But 1 day in space is equivalent to about a year on Earth's surface of radiation exposure. At the current time with our current technology, a trip to Mars for about 6 months one way gives you 700 times the radiation dose that you're supposed to have as a human being. So that, I think that doubles your risk of cancer, I'm pretty sure. There was a study between two twin astronauts, Scott Kelly and Mark Kelly, where Scott Kelly spent an extra year in space in the International Space Station, and he has significant DNA damage in comparison to his brother. So again, radiation is not just an iridian problem, and this is an active area of research in planetary science and in materials science and in textiles and all of these different things. In NASA and space science at large right now, because the sun is in fact a deadly laser. But how do we protect ourselves from the sun being a deadly laser? We have hydrogen-based materials like Kevlar and other polymers that can absorb and slow down cosmic rays. We also can look at the sun and monitor the space weather. We have about 7 to 8 minute window to figure out if there's a really massive event coming, so we can tell the astronauts like, okay, try to get into a better place within the spacecraft if you can. And usually that means the big storage units that we have in the International Space Station, you can use water, food, equipment, stuff like that. The more stuff between you and the outside, the better. And this ties into the coma thing. So Ryland was asleep on the Hail Mary for about 4.75 years, which is 13 Earth years almost because of time dilation, which is still a lot of exposure. If we can't even go 6 months without dramatically increasing our cancer risk, imagine going almost 5 years. So finally, some wibbly wobbly, timey-wimey stuff. So the way that this is explained in the book is that there is a coma gene that does not exist in real life that allows you to not get metabolic strain, metabolic strain or sedative toxicity. So in the book, Dr. Grace was the only person left with this gene, and so he's forced to join the mission. In the movie, he's just a specialist, and so then he is kind of forced to go along. But in reality, induced comas last weeks at most, and if you go longer than that, you're really at a lot of risk for like brain damage. And another thing to think about is that as soon as he woke up on the Hail Mary, he could stand. But imagine being still for like almost 5 years. You would not retain all of the muscle that he says he retains. Always muscles, I think is what he wrote on the whiteboard in the movie. So this is kind of like a Jack couldn't fit on the board with Rose problem. It serves to advance the plot. It is Hail Mary full of grace, not Hail Mary full of Yao and Yukina, the other astronauts. So we talked about this a little bit. The Hail Mary's journey was 5 years, but that was 13 Earth years. So how does that happen? When you're constantly accelerating, time moves differently for you than for someone at rest. And so that gets into Einstein's theories of general and special relativity, where we look at this equation here called the Lorentz transformation. So if we know that the Hail Mary's journey was 13 Earth years, and it took about 5 years for Ryland Grace to reach Tau Ceti, that means that they were traveling at about 92% the speed of light, thanks to the astrophage. But this is sort of an egregious oversimplification because they were accelerating the entire time they were going to Tau Ceti. But that's the end of the science. I want to say, all in all, this is a really, really awesome story about the resilience of the human spirit and the power of friendship. Humans love to be friends with everything. It's about the wonder of exploration and the beauty of the natural universe. So the physical sciences describe the laws of the cosmos, right? But art like this and humanity give it all meaning. So Project Hail Mary is an amazing book, it's an amazing movie, and I'm sure it's opened a lot of people's eyes to space science and space travel, and it's super awesome. I love this piece. So now I will take question if anyone has any. Thank you.
So, do we have any questions?
Can you go back to the radiation affecting humans real fast? You were saying something about it would affect violent race. Why?
So, okay, if we look at this image over here, I didn't have time to talk about this figure, but these are all the fuel tanks at the bottom of the canonical Hail Mary. The humans were stationed here in the center, and then the lab was up here at the top. So when they're in the centrifuge configuration, or as they're accelerating, there's still a lot of room for the astrophage to not absorb all of the incoming radiation. While Rocky's lab was surrounded by the fuel tanks, they are definitely being hit from multiple angles where they can get a lot more radiation.
This is book canon. I don't know if you showed the movie, but there's a pin there, like afterphage covering the ship. It's got both prevented.
Oh, I didn't know that. Okay.
There's like temperature sensitive all over to make sure there's no gap in the afterphage covering the whole ship.
Okay, good. I'm so glad. I kept looking things up about it and I couldn't find anything, but that's awesome. Thank you for sharing.
Hi, John.
Does the research to protect astronauts from radiation carry over to cancer research in general?
Honestly, at this point, I'm not sure. There's been a lot of defunding in science in particular recently, so I wonder how much research is being done in space science versus health science at this time. And I'm sure that the overlap is pretty small, but I don't really know if I can answer that question.
On a side note, next month we'll have one of the UCF researchers currently doing X-ray or space astronaut radiation science at UCF. So she can talk about bone density changes with radiation next month.
He's coming back because we couldn't hear, so I'm keeping on the presentation, but he's coming back.
I'm sure your presentation is great. So even when you go to an X-ray, where they're thyroid and organs, but they don't do that in space.
Oh, so you're saying like we don't wear like lead protective vests? There are different types of protective gear that the astronauts can wear. I think they've been testing some different radiation proofing vests, but imagine having to be in like microgravity and wear a lead vest all the time.
True. It could be very light. But I'm not sure if they have any. But I'm pretty sure they have them.
They're going to the depths of the station to hide from
And you can also think that lead is super heavy and it's really hard to launch. Whenever we launch things into space, we try to mitigate as much weight as possible. And there are other forms of radiation like gamma rays from galactic cosmic rays that are even more harmful than X-rays. So there's a lot of stuff that we have to worry about.
Yeah, the comet you went to infrared on the surface of the planet anyways.
My question is, in astrophase or astrophase is a big eater in the sense of only looking for CO2. Is there any other similar process to a planet that doesn't have CO2, or does it just only eat planets?
As far as I know, astrophage only eats CO2, but I think it could stand to reason that they could evolve to eat something else. Maybe they could evolve to metabolize methane instead. I don't know, because we saw in the movie that the Talmiba evolved to do different things as well. So it could stand that it's possible that the astrophage could do other things, but I think most of their science was based off of like photosynthesis and like those kinds of processes. So.
Do you have any more questions?
I was curious how many times you saw the movie, or did you get dialogue or the script, or were you quoting from the book? Because your quotes were spot on. Thank you for your comment.
So I saw the movie twice, but the quotes stuck with me the first time because they bothered me so much. The entire time I was like sitting in the movie being like, oh my god, I can't believe they said that. But yeah, I didn't check the movie scripts online or anything. I was just like, I know what they said.
Do you have any more questions?
So this question is about exoplanets. So I know about the transiting exoplanet method of finding them. How do we find them if there's not if that doesn't work? Like if the other solar system's edge is not aligned with ours. Are there other ways of finding exoplanets?
There are other ways of finding exoplanets, and John, as the exoplanet person, I'm giving this to you. Unless you don't want it.
I mean, I'm a theoretical atmosphere person. I don't do observational stuff, but I know there are at least 5 different methods. You can, a lot of the, like, you can look at the star and it has a wobble to it. And if that wobble is not predictable, that means there's an object there causing the wobble to not be predictable. And a lot of that can, and we are getting direct images these days now with JWST. So we do have some of the very first direct images of exoplanets that are basically plane on. So you can't, those are mostly gas giants, hot Jupiters. But as technology is getting better, we are able to see better, and the resolution is getting much better these days. So hopefully with HWO, Habitable World Observatory, we'll be able to directly image Earth-sized and maybe Mars-sized terrestrial planets around other star systems. But yeah, there's many different, I'm not familiar with all of them because I do theoretical work, but yeah, there's quite a few different ways to not use the transit method. And in fact, the transit method is becoming less and less popular as the technology is getting better and better, because the problem with stars is they're so variable. It's very, very hard to characterize a tiny atmosphere around an exoplanet when you have a giant star that you can't subtract out perfectly every time. So it's becoming a method that is slowly, sorry to anybody who's actually still doing that, but it is becoming a method that is less and less popular as time goes on.
I also want to point to the ALMA Observatory. It's an observatory in the Chilean mountains that is allowing us to image for the first time like planetary systems as they're being born. So we're getting like images of the gas disks and like the planets coming out of the gas disks as well. So that's been really, really cool recently.
Yeah, if you haven't seen ALMA images, they are beautiful. They are really spectacular. Do we have any more questions for our last speaker? Okay, let's give a round of applause.